Hello, my wonderful viewers. You're welcome to Understanding Chemistry of Nkechi. Today's topic will be looking at rates of chemical reaction. Alright. So when we talk about rate of chemical reaction, speed of chemical reaction, you know that some reactions occur very fast, some are very slow, some it can take years for the reaction to complete. Okay, looking at the following terms: chemical kinetics and reaction mechanism. So chemical kinetics is study of the rate of chemical reaction. That's chemical kinetics. Reaction mechanism is the route through which a reaction proceeds to yield products. That's a reaction mechanism. So you can say that rate of chemical reaction embodies the study of chemical kinetics and the reaction mechanism. So we're going to be looking at factors that affect rate of chemical reaction. So we're looking at factors affecting rate of chemical reaction. So number one is temperature. Concentration affects liquids and solids, whereas pressure is for gases. Physical state of the reacting species. So we're talking about surface area. Then catalyst. I think the density of light is among them. Density of light. Okay. Let's look at the effect of temperature. How does temperature increase the rate of chemical reaction? So increase in temperature leads to increase in the rate of chemical reaction. Decrease in temperature also leads to decrease in the rate of chemical reaction. What happens when you supply heat? When you supply energy in the form of heat to a reaction system? So what it simply means that those reacting particles will acquire kinetic energy. And once they acquire kinetic energy, their speed increases, which makes them to collide more often with one another. Whatever that leads to increase in collision or leads to increase in frequency of collision among the reactant particles will lead to increase in rate of chemical reaction. We can see the effect of decrease in temperature means decrease in the rate of chemical reaction. Refrigerator, works the principle of low temperature. What it means that it slows down the microorganisms that cause food spoilage. Let's look at the effect of concentration on the rate of chemical reaction. Concentration simply means the amount of solute in 1 dmq of solution. When you increase the concentration of the reaction, it means that there will be more collision among the reactant particles, which will lead to increase in the rate of chemical reaction. Whatever things that leads to increase in the collision among reactant particles will definitely lead to increase in chemical reaction. Okay, if I put 5 grams of zinc in 0.5 mole per dm cube of HCM, and in another vessel I put 5 grams of zinc in 2 mole per dm cube of the same acid HCl, which one do you think will react faster? The mass of the zinc is same, 5 grams, and you can see the concentration varies. This one is 0.5 mole per dm cube, this one is 2.0 or 2 mole per dm cube. This one has a higher concentration, higher concentration than this one. So this reaction will react faster than this particular one because of the effect of what? Concentration. So the higher the concentration of a reaction, the greater the rate of a chemical reaction. So for pressure, if we're talking about gases, when you increase the partial pressure of the reactant, it's going to lead to what? Increase in the rate of chemical reaction. Look at if you have a reacting vessel, and this is a gaseous reactant. It means that the volume of this is going to reduce. The higher the pressure, the lower the volume, and the greater the what? What means that if I put 80 grams of 80 kilogram of weight and press this thing down, the volume is going to reduce. So what happens to the reacting particles, the system, what happens to the system? It means that they now have a small space, isn't it? They are not gathered in a smaller space. which means there will be better collision, effective collision among those reactant particles. They're going to what? Hitting themselves, colliding with one another and with the walls of the container. So anything that leads to, greater increase in collision of reactant particles will lead to what? Increase in the rate of chemical reaction. So the higher the pressure, the higher the rate of chemical reaction. So let's look at another one, physical state of the reacting species. So we're talking about surface area. Increase in surface area leads to what? Increase in the rate of chemical reaction. How can one increase the surface area of the reactant? Of course, surface area, we're talking about solids. Is by subdividing that particle into smaller pieces or crushing it into powder. When you do that, you're increasing the surface area of those reactants. You're exposing that reactant to the other reactants. For example, if I react zinc powder or zinc dust with hydrochloric acid, and the same zinc lump or lump of zinc will take CL. The one that's going to react very faster is zinc powder, because the zinc powder is already exposed, has many surface in contact with the hydrochloric acid than this particular zinc lump. It's only just the ones on the surface that's reacting, which means it's going to take a longer time for the acid to get inside the zinc lump for the reaction to do what? To react. It will react slowly to everything what dissolves. But with this one, within 1 minute, the reaction is over. Okay, so we can also demonstrate the effect of surface area. When you burn log of wood and sawdust, which one among them going to between them, these two, is going to react very faster? The zinc dust more than what? Log of wood. Take a longer time for this wood to do what? To burn completely. The other one is also what? Seen in cube of sugar and powder sugar. If you dissolve the two in water, the powder sugar is going to do what? Dissolve faster than cube of sugar. Okay, if I give you a question like this, for example, magnesium reacts with hydrochloric acid to give magnesium chloride. So look at the reaction on the board. Magnesium reacts with hydrochloric acid to liberate hydrogen gas. If you're asked to state two factors that can increase the rate of chemical reaction of this reaction, of course, this magnesium is solid. If I increase the surface area of this solid, of this magnesium, the rate of chemical reaction is going to do what? Increase. The hydrochloric acid, if I increase the concentration of the acid, the reaction is going to do what? React very fast. Look at the effect of catalyst on the rate of chemical reaction. What's a catalyst? A catalyst is a substance that alters the rate of chemical reaction without itself. Let's look at the effect of catalyst on the rate of chemical reaction. What's a catalyst? A catalyst is a substance which alters the rate of chemical reaction, but this self does not undergo permanent change at the end of the reaction. So what it simply means that when you put 2 grams of catalyst, at the end of that reaction, you also have 2 grams. It will not decrease or affect that catalyst, because catalyst does not change. It does not affect the product that is being formed. Catalyst is what? Specific in action. Catalyst does not change the equilibrium position of a reversible reaction. So these are the characteristics of the catalyst. So let's look at this reaction. the composition of potassium triosochloride 5. Okay, look at this reaction. Okay, look at this reaction. In the production of oxygen gas, manganese 4 oxide is added to potassium triosochloride 5 as a catalyst. You can see on the bottom side, there's no manganese appearing here. So this manganese, you see any equation written like this, it shows that this substance acts as a catalyst. So with the addition of a catalyst, only a moderate heat is required. So this catalyst is acting as what? A positive catalyst by increasing the rate of chemical reaction. At the end, you also get the same mass of manganese 4 oxide that's being added at the end of the reaction. So catalyst increases the chemical reaction by lowering the activation energy. That's a very important point. Lowering the activation energy of the reaction. Activation energy of the reaction. Remember, if the activation energy is very high, it will be difficult for reaction to do or take place. Right? Reaction to do or take place. A spontaneous reaction has a very low activation energy. So when the reaction is very, very high, it means that reaction will be difficult to take place. So when you add a catalyst, it lowers that activation energy. So it makes the reaction to do what? Proceed fast. The reaction will complete within a short time. It was completed. So negative catalyst acts by doing what? Increasing the activation energy. So call those ones inhibitors. Example of inhibitor include this. Look at this acid. The commercial production of hydrogen peroxide. Phosphate 5 acids added to slow down the decomposition of what? Hydrogen peroxide. So in that case, it's acting as inhibitor. Alright. Let's look at a graph that shows what? A catalyzed reaction. So I want to say something. Any substance you add in a catalyst to enhance its performance, that substance is not the catalyst itself. It's what we call promoter. Promoters enhances what? Performance of a catalyst. Okay, look at this energy profile diagram of a catalyzed reaction. So look at this. This energy. This reaction coordinate. So this one is for exothermic reaction. The reactant is higher than the product. So in this case, the product is what? Higher than the reactant. That's endothermic reaction. So look at this. This is the activation energy. This is the catalyzed reaction. You can see how low the activation energy is what? Lowered. Because catalyst is added, it lowers the activation energy so that the reaction can proceed very faster. So this is the activation energy of the catalyzed reaction. So the other one, this higher one is what? Activation energy of uncatalyzed reaction. So whenever you are asked to draw the activation energy profile diagram for catalyzed reaction, you might not be asked to draw a catalyzed reaction. You can just put this reaction, for example. This one I put like this. And you're asked to draw the energy profile diagram of this. You don't need to ask what is it, what am I drawing for which one, what of reaction. This is a catalyst. What you simply need to do is just draw this catalyzed reaction and put this reactant here. Because using A plus B, you put this here. Instead of using 2C, you put your product here. So you can see the energy profile diagram of uncatalyzed reaction. So this is the enthalpy change. That's the heat content. So because the reactant is what? How do you get the enthalpy change? The one of product minus reactant. So when you do this, what is lower minus this? It must give you what? A negative what value. So the same for endothermic reaction, the same thing we did here. So you can see this is the uncatalyzed reaction, This is the catalyzed reaction. This one is what? Uncatalyzed. This substitute H means energy, activation energy. So this is the one for uncatalyzed reaction. So this is the one for catalyzed reaction. Alright. So rate of reaction can be defined as the change in concentration or volume, mass of the product or reactants per unit time. Or you can also say rate of a chemical reaction can be defined as the number of moles of the reactant converted or product formed per unit time, and the unit is mole per liter per seconds. So liter is represented as dm³. So mole per dm³ per seconds. It can also be, remember, mole is represented as this. The constant is capital M represents what? Mole per dm³. So let's look at this arbitrary reaction. A plus 2B. A reacts with 2B to give 2C. So you can see that what happens is that the reactant will disappear, isn't it? Then product is going to do what? Appear. When you react zinc with acid, what happens to that zinc? It will disappear. You see it again. You are seeing a zinc chloride and gas coming out, hydrogen gas. So reactants are going to do what? Disappear. Then products are going to do what? Appear. Alright. So remember, in every reaction, at the beginning of the reaction is very, very fast at the beginning. Then it gets to become slower, and at the end it ceases. So what happens is that we want to look at rate of disappearance of reactant A. So you want to put minus because the reactant is going to disappear to form product. So change in concentration of A, or change in time. Rate of disappearance of reactant B, you put minus sign, which signifies disappearance. So 1/2 because the coefficient is 2. So if I have 3, 1/3. If I have 4, 1/4. So 1/3 change in concentration of B, 1/3 change in time. So rate of appearance of products, and product is C, and the coefficient is what? 2. So 1/2 change in concentration of C, 1/the time. So rate of reaction is equals to this. Is equals to what? The one for B, and it's equals to one for what? C. The square bracket signifies concentration. Anytime you see this thing in chemistry, it means what? Concentration. Let's look at the graph of concentration against time. You can see that concentration decreases when the passage of time decreases. Even the one of product is going to increase with the passage of time. Product increases, the concentration of product increases with the passage of time. That of the reactant decreases with the passage of time. So let's look at this exercise. It was found during the decomposition reaction of ammonia that hydrogen was being formed at the rate of 0.058 mole per liter per seconds. So this is the question for the reaction. So question number 1, calculate the rate of decomposition of ammonia at the time of observation. Calculate the rate of formation of nitrogen at the time of observation. Calculate the rate of the reaction at the time of observation. Alright, so we're going to start with number 1. So you can see that hydrogen is being formed at the rate of 0.058. So I'm cleaning the board to have a space to solve it. Calculate the rate of decomposition of ammonia at the time of the observation. We are giving the value for the concentration of hydrogen. Hydrogen to be 0.058 mole per liter per seconds. And we're asked to find the rate of the composition of ammonia. So first of all, we're going to note the mole ratio. The mole ratio of ammonia and hydrogen is the ratio of 2:3. Okay, so let's write the equation for the disappearance of ammonia. So which is minus, remember the coefficient is 2, so 1/2 change in concentration of ammonia all over change in time equals to, so the one for hydrogen, I will not do this one for nitrogen. So the relationship is between ammonia and hydrogen. So the one for hydrogen is plus, because on the product side 1/3. So change in concentration of hydrogen gas all over change in time. So I have plus 1/3. So the value for the hydrogen is 0. I don't know if you put in bracket again. So 0.058 mole per dm³. So how do I get this thing? Consider ammonia, change consider ammonia all over time. This 2 is 1/2. This 2 is like this. This 1/2. This value is 1/2. So what it means that for me to have this change condition of ammonia over time, this 2 is going to do what? Multiply. Multiply. This is going to 2 is going to be here. So minus. So have these 2 multiply this, so 2 times 0.058 divided by 3. So change the concentration of ammonia Remember, we are asked to calculate the rate of decomposition of ammonia. Because the composition of ammonia, your value you're going to have here is negative sign. There was negative, you have removed that negative. That negative sign is going to come here. Because if it's reactant to decompose the reactant you are looking for, you must put a negative sign. So minus 0.039. So minus 0.39 mole per liter per seconds. Look at the minus because ammonia is on the reactant side. So this is question number 2. We have to calculate the rate of formation of nitrogen. Okay, look at this. This equation. Nitrogen is the product side plus change in concentration of nitrogen over time equals to. And compare nitrogen with hydrogen. You can also use ammonia and the nitrogen. So you get the same answer. So for the hydrogen, I put plus because on the product side. And 3 being the coefficient, 1/3 changing concentration of hydrogen all over time. Okay. So when I put the value here, hydrogen, we are giving the value to be 0.058. So 1/3 times 0.058 mole per liter per seconds. So there's nothing there again. There's no coefficient here. One of anything I will say I'm multiplying. So when I divide this thing, that will give me the answer. So change. The one for nitrogen will be so 0.058 divided by 3. So I'll be having 0.019 mole per liter per seconds. So this is the answer. So I want to say something. If, for example, the equation is a subjective question that whatever you solve does not matter, is the final answer, I'll give you points, not the solving. I have something like this, mole ratio of this being being 1 and this one is 3, and you're giving this one that is 3 the value. If you want to find this one that is here, this one that the mole ratio is 1, just divide it by 3, divide by 3, you get it. If you are giving value of this one and you are not giving value of this one, how do you get this one? Times this one, times that value that you give here, times it by 3, you have this one. If you are giving this value of this one, how do you find this one? That value I didn't give you here, times it by 2 to give you this. Simple. To save your time. So let's have question number 3. Okay, and this has something. Since this one is we're looking for nitrogen, and nitrogen is on the product side, I can as well put plus. So the question number 3 is to find the rate of the reaction. So rate of reaction. So remember the formula I gave for rate of reaction. Rate of reaction is equal to rate of the composition of ammonia, formation of nitrogen. Anyone will do to give you the same answer. I think rate of reaction is that value. The answer to the rate of reaction will give you the value of the one that doesn't have any coefficient. That the coefficient is 1. Is the value of that rate of reaction to give you the same answer as the one with coefficient is 1. So minus 1/2 change the concentration of ammonia by changing time equals to change the concentration of plus change the concentration of nitrogen all over time, which is equals to plus 1/3 concentration of hydrogen all over change in time. So the rate of reaction is equals to, so minus 1/2. So the answer we got for that of ammonia, for the ammonia we got 0.039. So I'll put the value and it's minus 0.039 equals to the one of nitrogen. The one of nitrogen we got 0.019 equals to the one of hydrogen. So this is the value for hydrogen own. So 1/3 times 0.058. So the rate of reaction will now be, if I minus times minus is plus, so 0.039 divided by 2, the value I will get will also be what? 0.019. The one of nitrogen 0.019. The one of hydrogen 0.058 divided by 3 will also give me 0.019. So the value is a positive value. Rate of reaction will always be positive, not minus. Because even when you have minus for ammonia, which is the reactant disappearing, the answer you got there is minus. So that minus you cancel. So that's the thing. So the value for the rate of, that's why I mentioned at that time, rate of reaction. If it's a subjective question, I ask what is the value of the rate of reaction. Instead of using this to waste your time, look for that one. The coefficient is 1. That's the answer. That value is the answer the center will get. Okay. For the reaction of ammonia, it was found that the formation of nitrogen was 0.27 mole per seconds. So this is the equation for the reaction. At what rate was water formed? So we're giving nitrogen and water. So we don't have anything to do with this. So we're going to start by writing the equation for the reaction, the formula. So this is positive. So product side plus, and the coefficient is 2. 1/2. The change in concentration of nitrogen divided by the change in time equals to the coefficient of water is 6. 1/6 change in water concentration all over change in time. So put our value. The value for the ammonia is given, which is 0.27. Then the one of water, I put it down. So how do I make this in such a formula? Is by multiplying this thing, this coefficient, this denominator, 6 times this value divided by 2. So that's what I did here. I just bring the one of water here. So equals to 6 times 0.27 divided by 2. So the answer is 0.81 mole per seconds. So if you ask to find the one of ammonia, say the same thing. Here be 1 over 4. 4 times 0.27 divided by 2. The one of oxygen, 3 times 0.27 divided by what? 2. Okay. Let's look at that question. Considering this reaction, A plus B to give C plus D, what is the rate of disappearance of B? Of B is equals to, you put B is reactant, you put the negative sign, put change in B all over change in time. So this is the answer. So very simple. If you ask to find the rate of appearance of C, you know what to do. Plus change the concentration of C divided by time. So look at this reaction above. If N2O was formed at the rate of 0.34 mole per liter, the rate of decomposition of nitrogen 2 oxide is dash. If this question is subjective, earlier, you are given the one of N2O to be 0. This one is 0.034. So if you have 1 mole of this, I have 3 moles. 0.034 will give you X. When you cross multiply, you have what? What it means simply means any value you have here, for you to get this value, it will be 3 times of this value. Simple. If you ask to find this one, since that the mole ratio are the same thing, the value will be the same. The rate of formation of NO will be what? So it will be 3 times of this value, 3 times of this value. So 3 times 0.034. So of course, because this reactant will disappear, don't forget that you're going to put the negative what value here, negative sign. So this is the answer. So the answer, if it's subjective, just this value is given, just do 3 times of this value. Whatever you get, don't forget that this is what reactant that will disappear. Just put what negative sign.